Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Okay, so in this lecture we are going to explain the direct determination of elastic curve from load distribution. So in previous lecture we have discussed how to find the slope and deflection using moment equation. Now in this lecture we are going to find out the slope and deflection by using the distributed load equation. So from our previous knowledge that we discussed in chapter number 5 and 6, that for a beam subjected to distributed load, dm over dx is equal to shear force. Clear? So if you again take the derivative of this equation, so d square m over dx square is equal to d over dx, and that is equal to minus w into x. So in short, the double derivative of movement with respect to x is equal to distributed load in the load direction. So d square m over dx square is equal to minus w into x, because you can see that if you take the derivative of double derivative of movement, it will be the distributed load. Now as we know that this movement x, from our earlier lecture we discussed that this moment x is equal to ei into d square y over dx square. Clear? So when you have this equation, if you take the double derivative of this moment with respect d square y or dx square. Clear? So if you take the double derivative of this movement, so this equation will be equal to ei d4 over dx4. I will write it over here, as we know that m of x is equal to ei into d square y over dx square. So if I take the twice derivative of this moment, so this equation will be equal to ei into d4 y over dx square. Clear? So this will be the equation. Now we know that this d square m over dx square is equal to minus w into x, and this d square mx over dx square is equal to this. So I will equate it. So this d square m over dx square is equal to ei d4 y over dx4 is equal to minus wx. I will also repeat that this is equal to ei d4 y over dx4, and this d square m over dx square is equal to minus w into x. So this is the same. So you can see this is same as I written over here. So you have this equation. Clear? I will write it ei d4 y over dx4 is equal to minus w into x. Now if you integrate this equation once, so you will get ei into d cube y over dx cube, and this will be equal to shear force, because you are going to take the integral, so integral of wx will be shear force, and that will be equal to minus integral of w into x dx plus c1. So this is the shear force equation. Now if you take the integral of this equation, so it will be equal to ei d square y over dx square is equal to movement. Now it will become movement, and this movement equation will be equal to minus integral of dx this is minus integral of dx into integral of wx dx plus c1x plus c2. Clear? So if you again take the integral of this moment equation, so the equation will be ei into dy by dx is equal to minus integral of dx into integral of dx into integral of wx into dx plus c half of c1x square plus c2x plus c3. Clear? Now if again you take the integral of this equation, so that will give you the slope. I will write it over here. So again if I have, okay, so if you take the fourth time derivative, clear, so the equation of this deflection will be equal to ei yx is equal to minus in 4 time integral of d 3 times integral of dx into integral of wx into dx plus 1 over 6 c1 cube plus 1 over 2 c2x square plus c3 into x plus c4. This is the same equation if you take the integral of this equation or the equation of slope. Clear? So you will get this equation. Now you can see that there are 4 unknowns constant, that is c1 c2 c3 and c4. In previously we have 2 constant and we use 2 boundary condition in order to find the unknown constant. So here we have 4 unknown constant, that is c1 c2 c3 and c4. So we will apply 4 boundary condition in order to find c1 c2 c3 and c4. Now you can see this is the cantilever beam that is acted upon by uniformly distributed load, and this is the beam that is under the uniformly distributed load, but it is simply supported beam. So as we have discussed that at fixed end deflection will be equal to 0 and slope will be also 0, while at free end there is no shear force, so shear force will be 0, and at free end there is no shear force, so bending moment will be also 0. Similarly, in case of simply supported beam, so you can see you have a pin support at point A and a rolling support at point B. So at x is equal to 0, you have deflection is equal to 0 and moment is equal to 0. Similarly, at point B, deflection is equal to 0. Point B means at x is equal to L, deflection is equal to 0 and moment will be equal to 0. Remember that whenever you have a pin support or rolling support, so at that points the deflection will be 0 and the moment will be 0, while in fixed end the deflection will be 0 and slope will be 0, while at the free end there will be no shear force and no moment at free end. Clear? So again you will use these boundary conditions. So for this cantilever beam, if this is a cantilever beam, so at x is equal to 0, so you will put y is equal to 0 in this equation. Similarly, at x is equal to 0, you will put slope is equal to 0 in this equation. I will show you in this equation. Clear? In this equation, so you will get value, and at x is equal to L, at x is equal to L, there will be no shear force and no bending moment, so you will put shear force will be equal to 0 at x is equal to N, and shear force and moment will be equal to 0 at x is equal to L. So when you apply the boundary condition on these 4 equations, so you will get C1, C2, C3 and C4. Now your concept will be clear if further if we solve concept application problem 9.2. The simply supported prismatic beam AB carries a uniformly distributed load W per unit length as shown here. Determine the equation of elastic curve and deflection, maximum deflection of beam. So you have to find the equation of elastic curve, that is slope as a function of x, deflection as a function of x, and then you have to find the maximum deflection of the beam. So this is the simply supported beam, that is there is a pin support at point A and a roller support at point B, and the loading is uniformly distributed load. The length of the beam is L. So we will solve this problem to find out the equation of elastic curve, and then we'll find the maximum deflection of the beam. So let's move further. Clear? So this is your beam, that is clear. There is a uniformly distributed load, and that uniformly distributed load is W. The length of the beam is L. This is point A and this is point B. Now as we discussed a little bit earlier, that we have formula this EI into D4 over D4y over dx4 is equal to distributed load W into X. Clear? So if you take the integral of this equation, so you will have EI into d cube y over dx cube, that is equal to equation of shear force, and that is equal to minus W into X plus C1. Clear? Now here this is W is a function of X, but if you integrate it, so it will be equal to minus W into X plus C1. Again, if you integrate it, this equation, the shear force equation, so you will have d square y over dx square will be equal to moment equation, and that is equal to minus 1 over 2 wx square plus c1 into x plus c2. Clear? So this is the moment equation. Okay. Now you will apply the boundary condition in order to find C1 and C2. So now for x is equal to 0 and x is equal to L. So we have seen that for x is equal to 0, moment will be 0. So at x is equal to 0, moment will be equal to 0, and at x is equal to L, moment will be equal to 0, because we have already told you that whenever you have pin support or roller support, so at that there will be no movement, but as there is a support, so there will be a reaction force at these two supports point. So we will apply this boundary condition at x is equal to 0, m is equal to 0, at x is equal to L, moment is equal to 0 in this equation. Let this equation is equation number 1. Let this is equation number 1. So we will put x is equal to 0, m is equal to 0 in equation number 1. We will get C2 is equal to 0, because x is equal to 0, so this term will be 0, this term will be equal to 0, so C2 will be equal to 0. Similarly, you have to put x is equal to L, at x is equal to L, moment will be equal to 0 in equation 1. So when you put it, C1 will be equal to half of W into L. Clear? you have to put it x is equal to L, C2 is equal to 0, so you will get C1 is equal to half of W into L. So now you have C1 and C2, you can put it in equation, put C1 and C2 in equation number 1. So we have EI into d square y over dx square will be equal to minus 1 over 2 wx square plus d square y over w minus 1 over 2 wx square plus c1 is 1 over 2 w into L into this x, and C2 is equal to 0. So you will get the moment equation like this one. Okay, now you can further integrate this equation. You can further integrate this equation. Let this is equation number 2. So you can further integrate this equation in order to find the slope and deflection equation. I will further integrate it. So when you further integrate this equation 2, so it will be like this one. I will write it over here. So EI into theta is equal to minus 1 over 6 wx cube plus 1 over 4 wl square wl into x square wl into x square plus c3. Now if you further integrate it, so we will get ei into y is equal to minus 1 over 24 wx4 plus 1 over 12 wlx cube plus c3 into x plus c4. Let this is your equation number 3, and we will use this equation to find out the C3 and C4. This is the deflection equation. Clear? So you can also see that from boundary condition, as we discussed it over here, at x is equal to 0, moment is equal to 0, and deflection is equal to 0. So at x is equal to L, deflection will also 0. So we will apply the boundary condition over here for, let me write, for x is equal to 0, deflection will be equal to 0, and put in equation 3. When you put x is equal to 0 and deflection is equal to 0, so C4 will be equal to 0. Clear? Similarly, x is equal to L, y deflection is equal to 0, and if we put in equation 3, so put x is equal to L, all the x should be replaced by L, and y is equal to 0, so you will get C3 will be equal to minus 1 over 24 W into L cube. Now you have C4 and C3 value, you can put in equation number 3. So the equation, I will write, put C3 and C4 in equation 3. So you will get EIY is equal to minus 1 over 24 WX4 plus 1 over 12 into WLX cube minus 1 over 24 WL cube into X. Clear? Okay. So this is the general equation for finding the elastic equation of elastic curve. You have divide this equation both side by EI, so you will get the equation that is equal to y, that is equation of elastic curve is equal to W over 24 EI into minus x4 plus 2l x cube minus l cube into x, and this is equation of, that this is equation 4 and this is equation of elastic curve, as y is equal to function of x. So we have find out the equation of elastic curve. Now in the part B it is given that find out the maximum deflection. So you can see that this beam is simply supported beam with uniformly distributed load. So load is symmetrical, so it means that deflection of maximum deflection will be at mid of the beam, that is x is equal to L by 2. So we will put x is equal to L by 2 in this equation. X will be equal to L by 2. So when you put, I will write over here and choose the another color. So put x is equal to L by 2 in equation 4. You will have to do this by yourself. So y maximum comes out to be 5 WL4 over 38 384 EI. So this is the maximum deflection of beam at x is equal to L by 2. Remember that if you have the beam in which the load is not symmetrical, so you have to take the dy by dx is equal to 0, and you will get the x value for which the deflection will be maximum, and then you will put it in the x value in deflection equation, and so you will get the maximum deflection. But here the beam is acted upon by symmetrical loading, so we can easily understand that the maximum deflection will be at half of the length of the beam. So at x is equal to L by 2. That's why we put x is equal to L by 2 in equation 4 in order to find the maximum deflection. I hope you have learned a lot from this lecture. Thank you for watching.